Hello, this is me again. Alrighty, and we're going to have our last little bit of video lesson for today. I'm going to take the notes here. We're going to try some problems, and then these notes will be posted, and then there'll be some classwork to go along with the earlier classwork, and then some homework for you guys to do. Alrighty, so here is the situation. Before last video, or the previous video, we talked about exponential word problems that involved this formula here. Okay, A is equal to P times 1 plus R to the T. If you haven't watched that video or haven't looked at those notes yet, you should go do that now. Don't do this video first. And also, I had a previous video in which we introduced the idea of Euler's constant E. Again, if you haven't looked at those notes or looked at that video yet, you should go back and do that one first. Kind of explains this number E that we're going to be working with in this video. Okay, so in any case, in previous problems, exponential growth problems involving money, we worked with this formula here, right? Now, but those were problems in money, in the world of investment and money, like savings accounts and retirement accounts and stuff like that, in which the growth would be incremental, like this. Every year, depending on what the annual percentage rate, there would be one new amount, one additional amount would be plunked in per year, right? So 10% of the previous year's amount would be added, and then another 10% the next year, and another 10% the next year, and another 10% the next year. But there's a lot of cases, which is kind of how it's done at banks with investments, okay? But there's a lot of investments, or not investments, but a lot of situations in which there is exponential growth or decay, in which the growth is smooth and continuous, not incremental. Rather than having a certain amount of new material added at certain stated intervals, it's sort of growing all the time. It's growing, in fact, continuously. So this is a case, so this we're going to talk about here right now for a few minutes about continuous exponential growth. And continuous also decay, by the way. Continuous exponential growth looks like this. We're going to use this formula here, where A, the ending amount, is equal to P, the initial amount, but we're going to use E to the RT. Completely a different kind of looking formula, where R is the growth rate percentage, like the annual percentage rate we had for the previous problems. T is the amount of time, and P is the initial amount, at time equals 0, and A is the amount after time T. Now, this formula goes for growth and decay, and we'll do some of each, okay? And we'll see how that works out. But it could be growing continuously, or it could be decaying continuously. And if you recall, this is like the rice grains that we had on the chessboard, and this was like the radioactive element, the element Z we had where it was decaying, okay? This formula, we're going to see, works for both situations, okay? Right, but first off, let's make sure we can find E on our calculators, okay? So we've got right here, slide it over here. Hopefully you can see it, turn it on. Remember how in the previous video, and I'm going to zoom in for a second here. In the previous video, we found we found ln. Oh, come on. Sorry, folks. There it is. We found ln, where here is the e. That's e, and then that little box there is where you'll put x. So remember, if we wanted to do, say, e to the third power, I'll write it right here. I would do, on my calculator, second ln, which is going to put the e there, and I'm going to put 6. Right? I can also do a negative, shift e to the negative 2 is, notice that's a fraction, or a decimal, about 0.135, right? So in an exponential expression, x can be negative. It's just in the log ones where x has to be positive. It can't be negative, okay? So if e is positive, if the exponent is p, exponent is positive, we're going to get a number bigger than 1. If the exponent here is negative, that's going to give us a value of less than 1. But in both cases, right, see, that was about 20. In both cases, even though this one's negative and that one's positive, these answers both come out to be positive. So in other words, there's no way that this exponential expression here can work out to be negative unless I put a negative sign out front. Okay, very good. So now we're going to use that to solve some continuous growth problems that are similar to the ones that we did before. Okay, oops, I'm going to zoom back out again here so we can see the whole page. Okay. Focus again. Very good. Okay, so let's say that we have this scenario here. We've got, say, a city whose initial population is 10,000 people. In, let's say, 1970. We happen to know that, through demographic data, that the city grows by 30% per year. Right? What will be the population? Here's the problem. What will be population in, say, 1990? Okay? So, now we're going to use, since the population grows incrementally, it's not like every year suddenly 30% of people move in all at one time. The city is growing continuously, and that 30% just accumulates all year. That's what we mean by continuous growth. So let's we're going to use this formula here. The initial population is 10,000, right? All right. And R, and again, we're always going to use decimals. So this is 30%. That changes to 0.30 when we move the decimal point, remember, 2 places to put it in its decimal form. Now T, what would T be? Well, we take 1970, it's simplest, we could use the year numbers, right? But it's simplest to think of 1970 as year 0, as T is equal to 0, because that's when we're starting our growth problem. That would mean 1990, can you see, is 20 years later. So 1990 is T equals to 20, right? So when we do these city growth problems, the initial year they give you, that will be year 0. And then the date, if they give you a date, it'll be that number of years after the initial date, right? So like 1980 would be 10 years, and 1995 would be 25 years. that make sense? Okay, very good. So now we just go ahead and we plunk the numbers in. The population, okay, 10,000 to start, and then E, then 0.3, and then 20. Okay? Hopefully you can see that okay. All right? Good. Now, I'm going to go ahead, and now we're going to plunk that into the calculator, right? Hopefully that's, I don't want to zoom in anymore, so I'm going to go ahead and leave it like that. Okay, hopefully you can see that okay. I'm going to use, remember we do the exponential part first. So I'm going to do Shift E, and then 0.3 times 20 in that exponential position. It's 403. Now I multiply it by the 10,000. Boom. So that looks like quite a lot, doesn't it? Right? So in 20 years, we're looking at 4,034,287 or 288 rounded up because they're whole people, right? It's pretty big growth. 30% per year is a lot of growth. Does that make sense? Okay, so that's how that goes. So that would be people. Notice since people come in whole units, that's why we're going to round up to 288. Alrighty, very good. So there's that. So that's kind of a city growth problem, and we'll have one of those on our classwork. Okay, so let's try another one. Let's say that we're talking about now a bacteria population. Okay? We've got a bacteria population, right? Okay, we're going to start with, let's say 3 bacteria. 3 little bacteria floating around in someone's bloodstream. Let's say this bacteria grows at a rate of 5% per hour. Okay, so it doubles, they're dividing, and they're growing at a rate such that the population grows by a cumulative rate of 5% per hour, right? Okay, so let's say how many bacteria are we going to have? Let's say only 24 hours, just one day. Okay, so we're still going to use the same formula here. P is equal to, or rather, A is equal to P times E to the RT, where P is the initial amount, which is going to be 3. E is our Euler's constant, 2.7. R is, in this case, it's going to be the hourly growth rate. So R can be, and T can be any time unit we want. In this formula, doesn't have to be years like in earlier formula. So R is going to be the hourly rate of 5%, and T is going to be the number of hours. Okay, so A is equal to, what is that, 3 E, and then 5%, that becomes 0.05, you understand. That's R. T is equal to 24, right? And then P was equal to 3. Better put that out there. So that's going to be now 0.05 times 24, right? So let's try that out. Okay. Shift E. 0.05 times 24. Right? That's 3.3, right? Times, and we started with 3 bacteria, and that's going to be about 9. So A, the amount after 24 hours would be 9.96 which we're going to round off to 10 bacteria. Does that make sense? Okay. Now, doesn't sound like a lot, but 5% is actually a very slow growth rate. Bacteria, especially when you're getting sick, the growth rate is much more than that. But anyway, so that's that. So that's that. Or let's say, here's another example. Let's say we have disease cases. I'll be right back. Let's say we have one observed disease case. Let's say it's the current coronavirus. We've got one that we've observed. And let's say that the growth rate happens to be, let's say, and this is something that we're seeing currently, 50% per day, which means that it doubles every two to 3 days. Okay, which is something that we're seeing currently here with the coronavirus. So 50% per day. So notice that with our problems here, the units don't have to be years. They just have to be consistent. So here we had growth rate per hour, and here we had our time units. This was after 24 hours, wasn't it, right? Okay, this is going to be 50% per day. Okay, so we had 1, so that's going to be P, the initial amount, right? R, that's going to be the growth rate. We're going to write that simply as 0.50. So how many observed cases will we see after, let's say, 30 days? See? Now you can see it. Sorry. After 30 days. Well, let's just see here. Okay, so this is going to be P is equal to 1 E 0.5 to the 30. See here? 0.5, that's the growth rate. 30 is the number of days, and T is going to be in whatever the time units are for the problem. Okay, so let's plunk that in and see what we've got. So that's shift E 0.5 times 30. Oopsie, don't need that parentheses. Times 1. And yes, that's right. Yes, that's right. That says, round it up, that is, let me kind of move it over here. Indeed, that is 3269017. Okay, round it up to 8. 3,269,000 cases and 18 cases after 30 days. Oh boy. So now maybe you have some idea of why medical professionals are yelling about this on the TV. One way to think about flattening the curve, when they talk about that, is to decrease that growth rate. 50% per day. Okay, now we're going to flip this around. Okay, so this is about example 2. I'd like to keep things numbered here. Example 3. We're going to flip this around, and we're going to go ahead and we are going to solve some of the time problems. Okay? Okay, so I'm going to flip this around, and same scenarios, so I don't have to think of a new scenario, but instead of given a time, figure out the ending amount, we're going to figure out how long it'll take things to grow. So back in the city there, okay, where in so this is going to be example 4, where in 1970, remember, the population was 10,000, right? Now the city manager is thinking ahead of time, or he or she is thinking, listen, we can see that we know that the city is growing by 30% per year. That's a lot. We have to plan for the future and make sure we've got enough roads and and hospitals and schools and libraries and fire hydrants and sidewalks and stuff and firehouses that we would need in order to serve the new people. So let's say, for example, he wants to know how long it'll take, how many years it'll take at this, assuming that this growth rate is constant, how long it'll take, how many years to double. This is called the doubling time, which is which, if you've been paying attention to the coronavirus news, is something that the health professionals have talked about in terms of how fast the COVID virus is growing. They'll tell you about, oh, there's a doubling time of 2 days or 3 days or 5 days or whatever that is, right? Anyway, so we want to know how many years it'll take this population to double, and we call that, in the world of math and also lots of other fields like in finance, we call that the doubling time. So if it doubles, that means the ending amount is 20,000. Okay, we're going to double from 10 to 20,000. So P, or rather A, we're calling A the eventual amount, right? And then R, that's still 0.30, the decimal version of 30%. And what are we solving for? T. Well, okay, so we set up our formula. It's still the same formula. A is equal to P times E to the RT. But now we're solving for T. And actually, there's going to be a shortcut here that'll make this easier to solve, because we have an ln, the natural log key on your calculator, that was solved before. So we're going to set the formula up first. 20,000 in for A, 10,000 in for P, E, 0.30 times T. Now, so we're going to again use log operations to spring the T out of that exponential position. So this swings around in front. So rather, oops, sorry, it's not the first thing we do. The first thing we do is we isolate the exponential part by dividing both sides by 10,000, right? So I'll write this here. All right, see, 10,000, 10,000, 10,000, right? That's equal to 2, is equal E to the 0.30 T. Now, if you remember when we solved this exponential equation before, we logged both sides. But now we get a shortcut, because we've got this ln log function on your calculator. Well, remember, log base ln is the same thing as log base e. That's what that means. It's like a shortcut. That means natural log, which is log base e. Well, all right. So what we're going to do is, instead of common log, we're going to ln both sides. ln 2 is equal to ln e to the 0.30 t. Well, that turns out to be very convenient, because these are direct inverses of each other. Okay, I'm going to write it over here, log base e of e to the 0.30 t. Well, remember that, what does log base e to the e work out to be? Well, that works out to be 1. Right? Remember how logarithms worked. E to the first power is equal to e. And that was one of our characteristics of logs. Log base x of x is equal to 1, right? The exponential, the log base canceled out what in effect is the exponential base, and you end up with just equal to 1. So what happens here is, those cancel entirely, and we end up with 0.30 t is equal to ln 2. Now, we divide both sides by 0.30, right? And t is equal to 0.30 t ln2 divided by 0.30, right? And on Mr. Calculator, here's the ln key that we worked with before. ln 2, close parentheses, divided by 0.3, boom, 2.3. So that would be 2.3 years. That's approximately equal to 2.31. So we're going to round that off as 2.3 years. So the city manager can expect, if the growth rate continues to be 30% per year, that in 2.31 years, the population of this city will have doubled. Better start preparing now, because that's not very long. Okay? All right, good. Now, by the way, this only happens when we're using ln. This canceling thing here only happens when we're doing ln and e. Usually the common log will not cancel out whatever exponential base you have, because the exponential base has to be the same as the log base in order for it to directly cancel. Okay? All right. So that's a nice shortcut we get with these continuous growth problems. All right. Now let's go back to the next scenario after that, which was the bacteria one. Okay, remember this is for this, I think, is example 5. This is the bacteria scenario we had previously, and we were starting with 3 bacteria, right? And we said that the growth rate per hour, the hourly growth rate, was 5%. And now our question is going to be, if that's the case, how long will it take to grow, that is the bacteria population, to grow to 1,000 bacteria? How long will that take? Well, keep in mind, when we mean how long, that's a time, right? Well, here the growth rate is in terms of hours, hourly growth rate. So when we calculate a t at the end, that number will also be in hours. So those will be the time units at the end. Okay, we're still using our same formula here, right? A is equal to P times e to the RT, right? But now we're going to put A is going to be 1,000, right? P is 3, E 0.05 T, right? Now again, we're going to go ahead here and we're going to ln both sides. So that's going to look like this. ln 1,000 equals to, oh, we're not going to do that first. Sorry, people. You're probably going, but Mr. Waters, you forgot something. Yes, we've got to divide by 3 first to get the E part by itself. So that's going to be 1,000 divided by 3, which is about 333.3 rounded off, because actually it repeats. So that's E to the 0.05 T, right? Now we ln both sides. ln 333.3 is equal to ln E 0.05 T, right? The ln and the E cancel each other. So we've got ln 333.3 is equal to 0.05 T. Okay? Divide both sides by 0.05, and that's ln 333.3 divided by 0.05. So we whip out Mr. Calculadora here. Ln 333.3, close parentheses, divided by 0.05, that is 116. So rounded up to 117, because again, bacteria come in whole units. So that's 116.18, which we round up to about 117 hours. Okay? Okay, so that's example 5. Now the last example we will do, before I let you go and set you loose on some classwork problems and homework, is we're going to go to the disease cases, right? Okay, remember we had the thing where it was increasing by 50% per day, right? Okay, so this is going to be example 6. Okay, disease. Okay, and we started out with one observed case, right? How long? And it's the growth rate was 50% per day, right? Which gave us an R technically of 0.50, right? Okay, so how long? In this case, how many days? Let's say that, okay, our hospital capacity is 4,000 diseases. Let's say our hospitals can hold 4,000 people. Okay, so we're planning here. We're the local authorities, we're the hospital people. You know, we're in charge of the hospitals, we're in charge of the local city, and we're thinking, well, okay, we have enough room for 4,000 people. How many days is it going to take in order to get to 4,000, assuming it continues to grow at 50% per day? Well, okay, A, that's 4,000. All right. The initial is 1, right? And then R, as I have there, is 0.5. So now we put that in, 4,000. And we're using the same formula here. Remember, it's going to be A is equal to P times E to the RT, right? So that's going to be 1, right? And E, 0.5 to the T. So far, so good? So now we divide by 1, which is divide both sides by 1, which is still going to give us 4,000 here, is equal to E to the 0.5T. Now we go ahead and we ln both sides, like we did before, is equal to ln e to the 0.5t. And oh look, again, ln e cancels out because the exponential base and the log base cancel each other. So now we've got ln 4,000 is equal to 0.5t. So t is equal to ln 4,000 divided by 0.5. ln 4,000 divided by 0.5, that is 16.58. Right, since days don't come in whole units, right? We could, I suppose, leave that as a decimal, but as you can see, that's going to be about 17 days to go from one case to 4,000 if the growth rate stays at 50% per day, which it is in some places right now. All right. So anyway, that's what's going on with exponential functions. Okay, and using logarithms to solve them. Now, these notes will be printed up, and you'll be able to look at it at your leisure, and you can look at this video again. Sorry that it's so long, but as you can see, we got stuff to do here. Okay, and I'm going to put this. I'm going to let you go. I'm going to put out some class work for you to try out, and then homework. Bye.